So that worked out to be 19 newtons, which works out to be 4.27 pounds. So the robot has a weight 5.96 pounds, and probably shouldn't be keeping three significant figures because I don't think my measurements are that accurate. But anyways, in the force to pull it horizontally was 4.27, but remember that it's only the traction wheels here that were supplying the resisting force, not the wheels in back. So we'll have to do the force analysis to figure out what the coefficient of friction is. So now in the next next part of the lab, we are going to do a static test, and we're going to determine the maximum height or the maximum angle that the robot can maintain static equilibrium. So in other words, it's going to come out of static equilibrium if it starts to slide, right, if there's not enough traction, or if it starts to tip, right? In other words, the wheels are locked, so it's not a question of having enough torque from the transmission. It's just a question of either stability, meaning we lose stability, it starts to tip, or we lose traction and it starts to slide. Okay, so I'm going to set this up and then we'll take a look at that. But what I want you to do, of course, is what you should be doing before you watch this video is, given what you know about the coefficient of friction, you should be able to predict, and given what you know about where the center of mass is, you should be able to predict whether it's in the, driving up forwards, or the forwards orientation, or backing up. You should be able to predict whether it's going to slide, what angle it would slide or tip at, and then what angle in the other orientation. Obviously, the smaller of those two, sliding and slipping, is the one that's going to pull it out of static equilibrium. Okay.